Okay, so let's jump right back in here. And so I'm going to give you the most important equations when it comes to actually dealing with oblique shocks. So here is my oblique shock once again. Here is my velocity, or my flow beforehand. So this is V1, this is M1, and then here it is afterwards. This is V2, and that is M2. And like last time, we have a tangential component which does not change, is constant for both of these. And I have a normal component which does change. I didn't draw this perfectly to scale, so forgive me that way. So we have W1 right here, and we also have our Mach number that's tangential to the flow, and that would be equal to W on this side, and my Mach number that's tangential to the flow. I'm just going to just get rid of the ones right here and the twos for those, because it is going to be the same. And I'm going to have my Mach number that is normal to the flow, and that does change, as well as U1. I'm going to have my Mach normal that is normal to the flow afterwards, and that is U2. Now, all of our relations are for the normal component. Okay, that's the only thing it works for. And so I'm talking right here about Mn2 and Mn1, okay? That is what it cares about. That's what it deals with. You're like, what about the tangential component? It doesn't do anything. The tangential component does not affect the flow. So all the pressure rise, density change, temperature change is coming from the normal component of my flow. Which brings me the question of, well, what is that normal component? Well, I can figure that out pretty simply. It's not too hard. Let me erase these guys, get them out of the way, because they're going to be obnoxious if I leave them there. There we go. First off, I need to remember what my angle is, and that angle right there to the shock wave itself is beta. That is from my initial flow direction. That's a very key point there, from my initial flow direction. And so I've got beta right there. As a note, if you have multiple oblique shock waves, you can have multiple different betas as well. So that's something we'll run into a little bit later on. We're doing some problems in our next class period. So if all my relations are for the normal component, I need to figure out how to find the normal component. That's not honestly all that bad. I was going to give you the relationship, though I could show it to you, but I'm not going to worry about that too much. Oh man, I feel like I should. Okay, we'll do that. So here is my before the flow triangle. There we go. I have my Mach number 1. I have Mn1 right here. Now, if you look at the triangle before, this right here is my oblique shock wave. And this angle right here is beta. So what is this angle? It's also beta. Who would have guessed? What? What? So if I wanted to find out what my normal Mach number is, well, I know I can use the sine function because that's right angle right there. And so I get that, let's see here, sine of beta is equal to my opposite over hypotenuse, so M normal 1 over M1. And so my normal Mach number before the shock wave is equal to my Mach number times sine of beta. So if I know my Mach number and that shock angle, I know what my normal Mach number is. And from that, I can do the rest of my equations. So that's every equation we had in our last section on normal shock waves. We had a whole bunch of equations. I'll give them to you again, but the only thing that has changed is I've gone from just saying M1 or M2 to Mn1 and Mn2. So just remember, like, if you're wondering where the derivation is, it's in your textbook. I didn't give you a big derivation for these things because it's not all that important. But all that's changed from this chapter to the last one is simply that I'm adding a normal because we only care about the normal component. So first off, what's the relationship between our actual normal Mach numbers? So that would be Mn1 N2 squared is equal to, and it's a big equation, which is why I suggest that if you're not going to put it into like some permanent like spreadsheet that does it for you, just go to the tables for it. It's going to be a lot easier on you. There we go. Okay, so that's the first one. That's relating our Mach number after the shock wave to our Mach number before the shock wave. It's a bear. You don't want to have to solve for it. So don't solve for it. Just don't do that. Just go to the tables. Seriously. Tables. Tables are your best friends in all these cases. Now, it is way faster if you have something built in Excel or in Python or some other MATLAB, some other programming language. Sure, that's way faster. That's great. If you don't have that built in, one, build it. It's a good little learning thing for programming. And two, otherwise just use the tables, because a lot of times tables can be faster unless you need a lot of information. Okay, then our density ratios. That's going to be equal to gamma plus 1 times the normal Mach number squared, all over 2 plus gamma minus 1 normal Mach number squared. Ooh. And our pressure is going to be very similar. So it's very similar, sorry. It's using the same tools, but not similar equation. My bad. Okay. 2 gamma plus 1 times our normal Mach number squared minus 1. I'm not going to bother to write out T2 over T1 because that is equal to P2 over P1, which I already gave you, times rho 2 over rho 1, which I already gave you, and it is just an absolute bear. It is a huge, huge, huge equation, and you just don't want to deal with it. So currently the only equation that I really think is actually helpful to you in the long run is our first one, okay? That is, let's see here, put it in green. This guy right here is a very helpful equation. The rest, tables are better. Now, the second thing that I will say is very, very, very helpful is our Mach number after we go through the shock wave. What is our Mach number? Not our normal Mach number, but our actual Mach number after the shock wave. So, something else we need to figure out. And I'll keep on moving down a little bit more. I think I should be able to go that far. So our Mach number after the shock wave, let's go through here. Okay, so I have this guy right here. I have my shock angle right there. That looks good. And I have some surface that was turning it. So this angle right here is my deflection angle. That's simply saying how much did it get turned from the horizontal, okay? That's my velocity, 2 and Mach 2 right there. This angle right here is beta. That is simply saying the angle from my initial direction to where the shock wave was, okay? To the shock wave. And so now I want to get my M2 in terms of what I know, which is my deflection angle, my shock angle, and also this component right here, which is Mn2. That's a right angle. And so I'm trying to figure out how to get this in terms of this. Well, it would help if I had one of those equations, right? It would help if I had one of those equations. And so hopefully I can figure it out in terms of one of those equations. And the great thing is, I can. I totally can. So how do I do that? Well, first I realized that this angle is also angle theta. Your flow is being deflected by the deflection angle. Okay. The second thing is I realized that this angle, that total angle, is beta, which means that this angle right here is beta minus theta, correct? Is that making sense to everybody so far? So now I have a definition for one of my angles inside my triangle. And since I have that definition, I can get everything in terms of it. So opposite over hypotenuse, that is, what function is that? Ah, it's sine. So sine of beta minus theta is going to be equal to opposite over hypotenuse, which is my normal Mach number, all over my actual Mach number. So I'm trying in this case to solve for m2, not for mn2. And so I do a little bit of algebra and I'll get that m2 is equal to my normal Mach number all over sine of beta minus theta. And this is after the shock wave, everybody. This is after the shock wave. And this is the second equation that I will tell you is actually very helpful. So don't forget that one. That one, you might have a table for it sometimes, but like in most cases, you're just going to need to plug it into your calculator. It's not terribly difficult to plug into your calculator. Okay. So after this, we're going to go into the most difficult equation that you will never, ever solve. Cool? I'll talk about a very important diagram that comes along with it.